So in this video, we want to look at the inverse sine function, or the arcsine function. So here's the basic idea. We've already developed the graph of the sine function, and what we want to do is look carefully at coming up with an inverse function for the sine function. And what we want to remember is that for a function to have an inverse, it has to be 1 to 1. So this was a big result that came out of a first course in pre-calculus. 1 to 1 functions have inverses. And for a function to be 1 to 1, what that means is that each output that the function has, has a unique input. So if we have an output, it can only have one input. Each output has a unique input. So for example, when I look at the sine function, if I think about an output of 1, I can see that there are lots of places where the outputs are 1. In fact, there's infinitely many angles for which the output is a 1. So the sine function is not 1 to 1. And the test that we developed in pre-calculus for testing whether a function was 1 to 1 was the horizontal line test. We said, hey, check to see if your function passes a horizontal line test. If it doesn't, that means that there are lots of places, perhaps there's at least 2 places if it doesn't, but in this case there's infinitely many places where a single output is generated by more than one input value. And the issue is when this happens that we want to remember that an inverse function, the graph of it is given by taking the original function and reflecting it in the line y equals x. So here's the line y equal x right here. So if we take the sine function and reflect it in the line y equal x, so there's the reflection of it, what we see is that because the sine function didn't pass the horizontal line test, when we reflected it, it didn't pass the vertical line test. And if you don't pass a vertical line test, then you're not a function. So our problem is, because the sine function is not 1 to 1, it does not have an inverse function. The reflection of the sine function in the line y equal x isn't a function. So that's what the problem is right now. The solution for this in pre-calc was to restrict the domain so that we have a function that can be reflected in the line y equal x. So before we restrict the domain, let's think about what we know about the sine function. We know that the sine function gives us the y coordinates as we rotate through some angle around the unit circle. It gives us the y coordinates. So if we have ordered pairs x and y, the sine function is the y coordinate that depends on the angle theta through which we rotated. So if I'm going to talk about the sine function, I'm going to say y, the outputs are y's, and if I use function notation, I should identify it's a function of theta, and the name of the function that plots the y coordinates is the sine function. So in function notation, we say, hey, it's sine of theta. So what we want to do is restrict the domain for sine theta so that we have a function that is 1 to 1. And what I want to notice is that if I start here at negative pi over 2 radians, remember this is the theta axis. This is where we plot our rotation around the unit circle. And this vertical output axis is going to be the y-axis because the outputs to the sine functions are y coordinates. So if I restrict my angles from negative pi over 2 to pi over 2 on the unit circle, what I see is that the graph of the sine function is going to be 1 to 1 over that restricted interval. So what we're going to do to get an inverse function is we're going to say, let's restrict the domain of the sine function. Let's only allow angles to run from negative pi over 2 to pi over 2, because over that interval, our function is a one-to-one function. So if I graph the function over just that interval, right there, and get rid of the rest of the function, I have a function so that when I reflect it in the line y equal x, here's the reflection, that reflection is still a function. So what I want to think about is if I'm restricting my domain for angles to negative pi over 2 to pi over 2, what outputs do I get? What outputs get generated over that domain? Well, the sine function over the interval from negative pi over 2 runs from a low of negative 1, because right here I have the ordered pair input negative pi over 2, output negative 1, and here I have the ordered pair input pi over 2, output positive 1. So I get a low point at negative 1 and a high point at 1. So the y values, my range, will run from a low of negative 1 to a high of 1. And what we want to identify is that's nice, because that's on the unit circle, that's every possible y value that can show up, a y coordinate that can show up as you run around the unit circle. So notice we're restricting our domain. Just damaged my unit circle. We're restricting our domain to run from pi over 2, right? This is pi over 2 position, from negative pi over 2. This is the negative pi over 2 position. So we're really restricting ourselves to quadrants 1 and 4 by running from negative pi, an angle of negative pi over 2 to pi over 2. That keeps us getting y coordinates in quadrants 1 and 4. So then I can ask myself, well, if I do this, what will the domain and range of the inverse function be? And what we want to remember from pre-calc is that the domain becomes the range, and the range becomes the domain on an inverse function. So the inverse right here is a reflection in the line y equal x, and the input's going to be a 1, and the output is going to be the angle that generated it. And here, this point is going to be input negative 1, output negative pi over 2. The inverse function. And what does the inverse function do? It get the inputs to the original function were angles theta. So the inverse function, the outputs are going to be angles theta. And we're going to give it a name. We're going to give it the traditional inverse name, F inverse. But the inputs aren't thetas. The inputs are the y values. The inputs become outputs. The outputs become inputs. And then we want to give it a name, so we can either use the traditional inverse notation, sine inverse of, and the inputs are the y values that generate the angle. And the other name that we use for the inverse function is Arcsine, and then we usually chop the e off, so we usually go Arcsine without the e, and it's arcsine of y. We're inputting y's, which means that the domain of the inverse function for sine, the arcsine, the domain is going to be the y values. The y values get to run from negative 1 to 1. You can put in any y value that you want from negative 1 to 1, and then the outputs, the range, will be the angles from the restricted domain. So the range will be angles from negative pi over 2 all the way up to pi over 2. So this has kind of a practical implication. So if I turn the sine function back on, let's say I input 1 into the arcsine. Well, there's lots of places where the y values are 1. Here at 5 pi over 2, here at negative 3 pi over 2, there's infinitely many places where the y value is 1. But when we plug a 1 into the arcsine function, it can only give us pi over 2. It can't give us any of the other angles that generate an output of pi over 2. So it's limited to giving us angle outputs on the restricted domain, negative pi over 2 to pi over 2.